Binomial expansion with Pascal's triangle. A binomial is a two-term polynomial. So we're just going to call the terms a and b, and we'll hold them together through addition as our definition for polynomial supports. Binomial expansion suggests that we're going to take this binomial and raise it to some power n. And for the expansion to occur, we want n to be an integer greater than or equal to 2, right? So if it's 0, there's no expansion. That overall value is 1. If it's 1, it's just whatever binomial is staring you right in the face. So we want it to be greater than or equal to 2 so that an expansion is required. And what do I mean by the expansion? Well, whatever the exponent value is, that's going to tell us how many times we have to multiply this binomial together. And given an n value large enough, you can see that multiplying these things over and over and over again can be rather time-consuming, inefficient, and there's a lot of room for error there. So is there a more efficient method? And the answer is yes. And we're going to use what's called Pascal's triangle. So to use that, we have to be able to derive Pascal's triangle on our own. And here's how you do it. Start with a 1. Each row will begin and end with a 1. So 1, then 1, 1. Start with a 1. Now, the number that goes next, or the number that will fall in between these two, is the sum of those two numbers, which is a 2, and then end the row with a 1. So the number of terms in each row is going to increase by 1, and you know it starts and ends with 1. It's just what are the other numbers going to be? It's going to be the sum of the two numbers above that place. So 3, 3, 1. So in this row I had 4 terms. The next row I expect 5 terms. Start with 1. The next one's 4, 6, 4, and 1. Where are these numbers coming from? Again, it's the sum of the two numbers above it. And you could repeat this process over and over and over again. But I won't do them all. Maybe do one more line. So that is how you derive Pascal's triangle. Now, the other thing you want to be able to do is identify what row each of these represents, because that's going to be important in the expansion. So the starting row we call row 0. Okay, then row 1, 2, 3, 4, 5, and 6, and so on. So again, this could be carried out for however many times you want. Now, how we use Pascal's triangle to expand the binomial is in the following way. It's going to be best done through an example. So actually, before I do an example, let's do it the old-fashioned way rather quickly, and then we'll see why Pascal's triangle is so much better when expanding a binomial. In fact, I'll choose a relatively simple binomial. Let's say we have x plus 2 to the 4th. We know that this requires the multiplication of 4 binomial terms to expand this. When we discuss multiplying polynomials, let's take care of the product of the first two. So if we multiply those out, we're going to get x squared plus 4x plus 4. Now let's multiply these two. So we're going to get x cubed plus 2x squared after the first distribution, plus 4x squared plus 8x after the second distribution, and the third distribution plus 4x plus 8. We'll combine like terms to get x cubed plus 6x squared plus 12x plus 8. So that is after we've done 3 multiplications, and then we have to do one final. And we're going to do x to the 4th plus 2x cubed, first distribution. Second, 6x cubed plus 12x squared plus 12x squared plus 24x plus 8x plus 16. Combine like terms, we'll get x to the 4th plus 8x cubed plus 24x squared plus 32x plus 16. So that took 6 lines of work and a lot of distributions to reach this final result. Let's jump back to Pascal's triangle to show how we can expand x plus 2 to the 4th in only 2 lines. So we see that the binomial comes in the form a plus b to the n. So the first things you want to be able to do is identify what a, b, and n are. Okay? So a standard form binomial, a plus b to the n. Standard form binomial expansion problem, I should say. The a term is x. The b term is positive 2. So if it was minus 2, we would have to identify b as a negative 2. and the n value is 4. The n value is going to tell you what row from Pascal's triangle to use. Okay, so we have to use row 4, which I already have labeled below. And once you identify the row you are using, you want to write those constants with some space in between. Okay, so we're going to do 1, and then a 4, and then a 6, and then a 4, and then a 1. So we want some space because we're going to put some things next to these numbers. And the things we're going to put next to those numbers are the a and b's through multiplication. So next to the 1, I'm going to do a, I'm going to do b. And then we're adding these things together, so we can do pluses in front of all these as well if you want, right from the get-go. And insert a and b next to the coefficient you found from that row in Pascal's triangle. The last thing you want to do is insert the necessary exponents. The exponents for your a, so we'll make a note, exponents descend. For b, the exponents ascend. Okay? Starting from the n value or starting from 0. So we'll say descend from n or ascend from 0. So these are the notes you want to have for that binomial expansion. So here we go. Let's insert the exponent values for the a. So we start at n, 4, and it descends. So 4, 3, 2, 1, 0. For the b term, it's going to ascend from 0. So 0, 1, 2, 3, 4. Now all we have to do is simplify this. So what does that first term simplify to? We have 1 times x to the 4th times 2 to the 0. Anything to the 0 is 1, so we're going to have x to the 4th plus 4 times x cubed times 2, which is 8x cubed. Then we have 6x squared 2 to the 2nd, which is 4 times 6 is 24x squared. Then we have 4x, 2 to the 3rd is 8, so 32x. And then anything to the 0 is 1, so 1 times 2 to the 4th is 16. So in 2 lines of work, we were able to expand that binomial and get the same result as we did before without any of that crazy distribution and a need to combine like terms. So I'm going to do one more slightly more complicated one. Let's say we're doing, and I'm not going to do the actual expansion, but let's say we have negative 3x, say plus 1 to the 5th. So we're going to have to generate what our a is. So a is equal to negative 3x. B is equal to, actually we can even assign a variable to b. Let's say we're doing, let's do something a little more crazy. Let's say we're doing something like 2y. I'm going to the 5th. Okay, so that looks pretty intimidating. So b is going to be positive 2y, and then our n value is 5. So we're going to have to come up with the 5th row. So row 0, row 1, row 2, row 3, row 4, and then row 5. So we're going to need our calculator for this one for sure, but let's write our row 5 with some space. I'm going to do plus 5, plus 10, plus 10, plus 5, and then plus 1. And attached to that, we're going to put our a's and b's. So a is negative 3x 2y, negative 3x 2y, negative 3x 2y, and I'll repeat. Then we said once we have our a and b's and our coefficients that came from Pascal's triangle written down, the exponents for a descend from n. So we're going to start at 5, 4, 3, 2, 1, 0. And the exponents for b ascend from 0. 2, 3, 4, 5. Okay. Now we're going to simplify this. So I'm going to have my calculator ready because we're going to have to do some computations that don't look too fun. But the first one, Anything to the 0 is 1. So we have 1 times negative 3x to the fifth. So negative 3x to the fifth, we have to do negative 3 to the fifth, which is negative 243 x to the fifth. So that's the simplification of the first term. Then we're going to have negative 3x to the fourth. So if we do negative 3 raised to the power of 4, we're going to get 81. But we have to multiply that by 5 and then multiply that by 2. We're going to get 810. So that's when I take care of the constants. And then the variables, x to the fourth, y. Next term, we have to do 10 times negative 3 to the third times 2 squared. That's going to get me the constant for this next term. And I already know that I'm going to have an x cubed y squared. So in my calculator, I'm going to do that computation I have written in blue. So 10 times negative 3 to the third, and then 2 squared is 4. So times 4, we're going to get negative 1080. The next one, to figure out the constant, we're going to do 10 times negative 3 squared times 2 to the third. So we have 9 times 8, which is 72, times 10, which is 720. So plus 720, and we're going to get x squared y to the third. So don't forget about those variables there. The next term, we're going to have, to get the constant, 5 times negative 3 to the first times 2 to the fourth. So 2 to the fourth is 16, times 5 is 80, and then times negative 3 is negative 240. Let's just double check that. Yep, negative 240. And then we have x raised to the power of 1, y raised to the power of 4. And then lastly, anything to the 0 is 1, so the last one not too bad. 2 to the fifth is 32, and then y to the fifth. So again, in 2 lines, these are some pretty crazy numbers here, but we were able to expand that binomial as opposed to multiplying that thing out 5 times. So there's your binomial expansion. Remember the key in this, which is important, and you'll see that I've been doing this, is when I figure out what the constant coefficient of each finalized term should be, we need to make sure we're raising those terms to whatever exponent it is. So a common mistake is when people see 3x to the fifth, they say, oh, that's just this. Okay? That 5 has to distribute into both terms. So we have to raise that negative 3 to the power of 5. Okay? So in this case, we're going to get negative 3 to the fifth times 2 to the 0. And that's where that first term came from. We're going to get negative 3 to the fourth times 2 to the first times 5. So there you have all the ways that those constant coefficients were calculated. Important to take into account those exponent values. But there's one that's a little more complicated, a little more crazy, but using Pascal's triangle to expand that binomial. Pretty cool trick. Will you ever have to do something like that? Not sure. But something like we did originally, the x plus 2 to the fourth, that's something you might come across. And although the calculation by hand, doing all the multiplication out like we started with, is not overly complicated, the number of steps leaves a greater margin for error as opposed to if we have the tool of Pascal's triangle, we can do this thing in 2 lines.